AI vision models are beginning to use generative backbones not to create images or video, but to directly read depth, geometry, segmentation, and pose. By reusing token spaces and spatiotemporal priors from systems like Black Forest Labs' FLUX-Klein and WAN 2.1, researchers are making perception faster, more adaptable, and less dependent on task-specific architectures. The broader shift is clear. Foundation generators are becoming general-purpose world models. We'll unpack why direct readout works, how it improves CAD alignment, and why video generation may be a powerful route to general visual intelligence. Let's explore the first paper, From RGB Generation to Dense Field Readout, Pixel Space Dense Prediction with Text to Image Models. Researchers at UCSD and HKUST propose Rechannel, a way to repurpose Black Forest Labs' FLUX-Klein text-to-image DIT for dense prediction without generating an image-like target. The method keeps the VAE encoder so RGB inputs remain compatible with the pre-trained distribution, adapts the frozen transformer using task-specific LoRa, and applies a shared token local linear head of about 33K parameters to read each spatial token directly into a pixel space patch. This removes the target-side VAE decoder and treats the DIT token lattice as a carrier for task-native fields such as depth, surface normals, alpha mats, referring segmentation, pose heat maps, and saliency. Across 6 tasks and more than a dozen benchmarks, Rechannel 9B achieves a kitty depth ABSREL of 0.063, trimap-free, matting SAD of 5.69 on P3M 500p, and average referring segmentation CIOU of 82 on the RefCoco family. It also reaches 79.2 AP on Coco pose estimation. In a matched FLUX-Klein 4B comparison, direct readout runs in 47.7 milliseconds, while an edit-based latent decoding pipeline takes 118.1 milliseconds, making Rechannel 2.48 times faster while remaining more accurate. Ablations show that LoRa adaptation and a strong pre-trained prior are essential, whereas larger spatial heads and full fine-tuning do not improve the compact readout interface. Let's explore the second paper, Souffleca Scaling Up Feature Learning for CAD to Image Alignment. Souffleca, from researchers at the University of Luxembourg and Universidad de Zaragoza, addresses zero-shot CAD to image alignment, estimating an object's 9D rotation, translation, and anisotropic scale from one RGB image. Its central idea is to convert appearance-oriented foundation features into geometry-aware descriptors by training a lightweight NOC head over 674K images from 12 real and synthetic datasets using a frozen Doomby encoder and dense prediction transformer. At inference, the NOC head is discarded, while compact 384-dimensional features support mutual K-nearest neighbor matching, anisotropic scale estimation with iteratively reweighted least squares, geometric consensus filtering, and ransack-based Procrustes registration. On ScanNet 25K, Souffleca reaches 33.4% category accuracy and 42.3% instance accuracy, exceeding ZeroCAD by 10.3 and 12.2 percentage points, and even surpassing fully supervised baselines. On the DiffCAD split, it achieves 36.1% and 44.8% category and instance accuracy, more than doubling ZeroCAD's performance. The system avoids iterative pose refinement and runs in 0.53 seconds per object with 2,178 megabytes of GPU memory on an NVIDIA RTX 5090. Experiments on occluded, inexact CAD retrieval using CO3D show stronger generalization than DNOF 3, L, Doomb, and Diorama, although CAD retrieval remains the main bottleneck for a fully zero-shot pipeline. Let's explore the third paper. Video generation models are general-purpose vision learners. Researchers at Google DeepMind, the University of Toronto, UCL, Oxford, MIT, and Lund University propose Genception, arguing that large-scale text-to-video generation can serve as a general-purpose pre-training objective for computer vision. Built on the OpenWeight's WAN 2.1 diffusion model, Genception converts iterative denoising into a single-step feed-forward predictor. Clean video latents enter a DT at time step 0, and text prompts select outputs such as depth, surface normals, segmentation, camera pose, and 2D or 3D key points. Dense targets share an RGB space representation and a unified L2 loss, while sparse predictions use lightweight learnable tokens. Training relies mainly on 7,500 synthetic human videos rendered from 800 render people assets and 200 CMU motion capture motion. Across benchmarks, the 14B generalist reaches an average depth ABS-REL of 0.071, competitive with specialized systems including Depth Anything 3, D4RT, VGGT, Omega, SAM3, Sapiens, David, Genmo, and Lotus 2, while outperforming VJEPA and VideoMay V2 under comparable settings. The model also matches leading depth and geometry systems using 7 times to 500 times less training data, and scales with model size and dataset volume. Removing WAN 2.1's 50-step sampling yields, 592S inference at 13.6 frames per second for the 1.3B version on 1v6 eTPU. Despite training primarily on synthetic human footage, Genception transfers to real videos, multiple instances, animals, robots, and other unseen articulated objects, suggesting that video generators encode reusable spatiotemporal and physical world priors rather than serving only as synthesis engines. That's a wrap on today's AI paper highlights. Thanks for watching.